Okay, hello. Today's problem is check completeness of a binary tree. I already wrote some solution in a previous video. Let me remove that. I'll try to do that again. I failed to record the previous video, so I'll just remove it and try to solve it again within like 20 minutes. So the problem statement is the following. I have like a binary tree. And I need to check if it's complete. By completeness, they mean on every level we have factor of 2 nodes. Like on the first level, on like 0 level, have 1 node to the power of 0. On the second level, we have 2 to the power of 1 nodes 2. And on the last level, we might have like less than 2 to the power of level. But they all should be located on the left side of the binary tree. So this one is valid because all the nodes are occupied or sequential places without gaps. And if I go to this tree, there is a gap. The left child for the parent's tree is missing, and it means this is not complete binary tree. So this is pretty, I would say, basic if I would solve it with BFS. So to solve it with BFS, I'm gonna have a queue, tree node, queue equals new queue, let's say linked list. And then what I'm gonna have the idea is to have the variable, kind of variable that will tell me, okay, so this one, let's say, we have, let's say, this variable that has flag variable has maybe gap or like end of tree, and whenever I see the child element equal null, I'll set is end of EOT, is end of tree equals true, and then I'm gonna check all the following children, and all the following children should be null. So if I check the children for 3 after, so initially this child gonna be null, so I flip the is end of and is, okay. So I'll call this flag is end of 3, and then it is a true or false. And then here I'm gonna flip it to from false to true. Initially it's false, and whenever I see the null child, I'm gonna flip it to true, and then all the following childs for the nodes in the queue should have like null, should be null. So if I check the children for 4, they all null. If I check the children for 5, they all null also. And then if I check the children for 6, they also null. How it's gonna work for the second image? So for the second image, I have again this is. Okay, is end of tree equals true, equals false initially, end of tree here, both children are not null, so end of tree false. Here, like end of tree false on the left. It was false on the left, false on the right, then false on the left for the 2, then false on the right for the 2 right children, and then it becomes true here because the left child of the tree is a null, and whenever I flip it, I start checking if the following children are null, and I go to the child 7, and here the flag is end of tree true, and it's actually not null. The right child is not null, so I return false. This tree is not complete. So there, generally I'm gonna have a queue, and if root, say queue offer root, and then while queue is not empty, I'm gonna have this int level equals queue dot size, and then for int I equal 0 I less than L I plus plus, then queue dot poll, and initially gonna have the flag is end of tree equals false, and then I'm gonna poll the tree node node equals q poll, and then I'm gonna check if node dot left equals null, then is end of tree equals true, and then I'm gonna check if is end of tree true, then I'm gonna check if node dot left not equal null, and return false. And then the same procedure is if node dot right equal null. I'm gonna do update is end of tree equals true, and then if is end of tree true, and if node dot right not equal null, then return false. Okay, that's it. And then in the end, I want to return true. And then also I need else here q.offer node.left, and here also else q.offer node.right to continue. Like this is the algorithm here, BFS. Let me think about if there are any errors here. Q. So in case root is null, what should I do here? I'll say if root not equal null, I'll do q.offer. Otherwise, I'll go through the algorithm, q gonna be empty, and finally I'm gonna return true. So I assume that empty tree is complete tree. Okay, let me run it. Okay, let's check it out. And yeah, that's it. I have a second idea how to can run the, let me double check if I'm recording. Yeah, I have a second idea how to run BFS for this case. So let's assume I have the same tree here. Let's say here, and I wanna count the nodes, and so the counting goes like this. First, I'm gonna count the nodes like 1, 2, 3, 4, 5, 6. So I have totally 6 nodes, and the counting for the children should go like this. So 1 gonna have nodes. I expect them to have 1 multiplied by 2 and 1 multiplied by 2 plus 1. And then for the 2 it's gonna be the same. So for the 2 the numbering gonna be like this. It's gonna be 1, it's gonna be 2, 3. For the 2 ID is gonna be 2 multiplied by 2 children and 2 multiplied by 2 plus 1. So it's like 4 and 5 IDs. So let's assume we're gonna have like different tree with different like values. I just don't wanna confuse everybody with, let's say we have 5, say, and 6, 7, 10, 11, 12, and then here 45. So the ID for the I wonder where is this uh, option to change the whites or color. Oh, okay. So 6, 7, let's say 42. Here we have 33. Here I have 21. Here I have 35. Say I have IDs. ID for the root one gonna be 1. ID for the children of the root gonna be 2 and 3. ID for the children of 2 gonna be 4 and 5. And IDs for the children of 3 gonna be 6 and then 7. So the total number of elements is gonna have like I'm gonna have six elements here, and let's say we have like the second example of the same kind of tree, but that's not complete. 21 and then let's say 35. So the counter, let's say we have a counter here, like global counter for the IDs, and I'm gonna assign IDs like to the children. So for the one, I'm gonna assign one for the root 1, for the 2 2, for the 3 3, for the 2 I'm gonna assign 4 5, and for this now I'm gonna assign 6 7, and then if the actual counter whenever I land gonna be less than no, it's gonna be need DFS. So I need to go through somehow. Yeah, go through. So okay, so I'm assigning like 7, and 7 gonna be greater than 6. Okay. Yeah, so the first iteration, count all nodes in tree. Nodes in tree. And then second step, just go through the tree and assign the IDs. And whenever the actual ID gonna be greater than count, it's gonna mean that there are some gaps that basically pushed their kind of pushed yeah, push the nodes lower, and they are not that dense. So for this, first I'm gonna do this public, like private int count tree node if node equals null, return 0. If node left, okay. return 1 plus count node dot left plus count node dot right. Something like this, and then int nodes equal node count equal count for the root, and then I'm gonna do this private boolean DFS, and then I'm gonna assign the IDs 3 node, and then ID, int ID, and then int count, and then for the if let's say no root equals now if not equals now, let's say return true. And then for the all subsequent combinations, I'm gonna do the following. Return DFS node dot left. Let's say if ID is greater than count, return false. Then DFS node left, and then ID multiplied by 2, and then count, then and DFS node dot right, ID multiplied by 2 plus 1, and then count. Something like this. Yeah, a little bit better. Okay, I guess let me check the timing. So the timing is 23 minutes. I guess it's past. I managed to solve this problem with giving two solutions, BFS, DFS. Yeah, that's it.